Hey guys, hello everyone and welcome to the channel and welcome to a new series of videos which I'm going to start from today onwards, and these series of videos will continue till the upcoming CSIR NET exam. This series is called 10 challenging question series, and in this series I'm going to take 10 very different type of questions, 10 questions which are little challenging from a particular topic. And these all questions are going to be new questions. They are not going to be previous year's questions. They are not going to be something from from GATE or CSIR NET. They are not going to be like that. They are totally new questions. And from where I am taking these questions, I am taking it from my ebook which I have recently launched on 1000 plus new question series. Like that ebook contains 1000 plus new questions on different topics of chemistry. So that's a new series which a new ebook which I have launched, and more about that ebook is there in a video. I have linked it in the I button. If you want to purchase that ebook, the link is there in the description of this video. You can reach out there. All these questions you will get, and there are more questions from it. Okay, I'm just taking 10 questions from a particular topic from that particular ebook. Now today's video will be 10 challenging questions on organic spectroscopy. I don't have to explain that how important organic spectroscopy is, and there are so many questions which every year you will get from this particular topic in CSIR NET. At least 2 to 3 questions you will get from this particular topic. So I am going to take 10 questions which are little different, which are not like usual type of questions from this topic. I am going to take questions from also from UV visibles, from NMR, little bit of IR is also going to be included. So all the topics which are there in organic spectroscopy are going to be included over here. Better way to make these videos more effective for your preparation is that when I'm going to take a question and when I'm going to explain it, in between that you can pause the video and you can try to solve that question on your own. Okay, in that case you will be able to understand that whether you know that concept, whether you are able to solve that question, and whether the answer or the explanation which I am giving is going to match yours or not. Okay, so that's how you can do it, and that's what I will recommend you to do. Now let's start this video. So hopefully if you will give a lot of support to this particular series, I'll continue this and I'll make more frequent videos on these 10 challenging questions. So let's start from organic spectroscopy and let's take the first question for this particular video. Alright, so let's take this first question over here. It says that the correct relationship between lambda and epsilon values for the compound shown below. So these are the two compounds which are given to you. They are asking about the relationship between lambda, that is the wavelength, and epsilon, which is the absorptivity, right? The molar absorptivity of the molecule. So what is the relationship between both of them for these two molecules? Try to solve it on your own. Pause the video, think about it, what could be the correct answer, and then I'm going to explain you. Okay. Alright, so let's look upon the solution of it. So basically, if you look upon both these molecules, the basic difference which you can see is this is a homoannular diene, right? Homoannular diene, and this one is heteroannular diene. Now this is pretty simple to understand. If you have studied UV visible spectroscopy, you might know about these terms. Homoannular diene has more lambda max compared to heteroannular diene. The base values for both of them is of course different. So you don't have to actually remember the things, but in case if you want to remember, or in case if you want to see that, you can you have the base value for homoannular diene as 256, and that's what you can use. Heteroannular diene is 217. So that's the basic difference between both of them. In that case, you will find out that homoannular diene will give you more lambda max, right? So in this case, in the case of homoannular diene, you will have more lambda max. So lambda max of first will be greater than lambda max of second. This is quite clear. Just with the help of the system, we can understand homoannular diene, because the conjugation over here is much more favored than the conjugation over here, and that's why this particular one is more this is going to have so more conjugation means more lambda max. So that's why now you can consider that your option number A is not correct and option number D is not correct. Okay, these two options you can simply cancel out. Now let's look upon epsilon values. So there is a basic relationship. If you don't know about it, just make a note of it, that lambda max of a particular system is inversely proportional to epsilon of that particular molecule. Okay, because epsilon depends upon the intensity of absorption, so lambda is inversely proportional to intensity as well. So this is the relationship which we have. Now considering that relationship, if lambda 1 is greater than lambda 2, and since epsilon is inversely proportional to that, so I can simply say that epsilon for the first is going to be smaller than the epsilon for second. Now this, both the terms like this thing and this thing is both given correctly in option number C, and that's why option C becomes correct choice for this particular question. It was simple, but this type of question has not been asked in CSIR NET. That's why I have given this over here. Let's take another question. Alright, now here it is from mass spectrometry. It says that the conversion of M by Z 164 to 105, right, is possible for the following compound through. So this is the compound given to you. Right now if you calculate its M by Z, it's 164, but they are telling you that it can be converted into something which we don't know, and it has M by Z of 105. Now how you can do that? There are options like McLafferty rearrangement followed by alpha cleavage, then there is alpha cleavage itself, then both A and B, and the last one is only McLafferty rearrangement. So let's try to look upon it. First of all, pause the video and think about it, how this can be done, okay, and whether it follows the conditions and all, and how it is going to be done. And now I'll explain you that how you can actually solve it. So if you look upon this particular molecule, it's a ester group over here, and if you see, so this is this is a particular molecule. This is alpha carbon, this is alpha position, beta and gamma, right? So you have gamma position and you have gamma hydrogens over here. Now whenever you have gamma hydrogen, in that case you all know that there is possibility of McLafferty rearrangement, and that can basically happen over here. And due to that, this particular molecule can be broken up, or it can undergo McLafferty rearrangement. If you consider drawing the mechanism for that, you can think of it like this, okay. After this particular thing, this will be like double bond O, and then you will have, along with it, you are going to have so this is what we are expecting, right? So this is what happens after McLafferty rearrangement. And now if I apply alpha cleavage on this, so alpha cleavage is going to remove one of this OH group, and this is alpha because this is alpha bond, right? So this is going to undergo alpha cleavage, and you are going to have something like this, C triple bond O. Now over here if you see the M by Z value for that, so for benzene we are going to for phenyl group we are going to have M by Z value of 77, and along with that you have carbon, which is going to have 12 plus 16. If you add all of them, you are going to have this as 105, right? So yeah, you have got that, because yeah, this is going to be 28, and yeah, correct. So you are going to have 105. So you have actually converted from 164 to 105. And how you have done? You have done first of all McLafferty rearrangement, and then you have followed it by alpha cleavage. So this is one of the probable things. So option A is correct, that you can undergo, like you can first of all undergo McLafferty, and then you can undergo alpha cleavage to get the answer. But is it possible to make the molecule directly through alpha cleavage? Yes, that is also true. If you break this particular bond, this is alpha bond, right? This is alpha atom or alpha group. So this bond can break, and direct alpha cleavage, if you do alpha cleavage, in that case as well, you are going to get the same molecule, which is C triple bond O, and along with that you will get CH3, C double bond O, CH3, right? So this is what you are going to expect to get over here. So that means that both like from both the cases, like by doing alpha cleavage as well, or by doing McLafferty followed by alpha cleavage, in both the cases you are actually going to get the species of mass 105. So both A and B are correct option. Your correct answer becomes option number C. So option C is the correct choice for this particular question. I hope you understood what is happening in this. Let's see the next question now. All right, here comes the classic like spectroscopy, organic spectroscopy type question. It says that the reaction of an epoxy ketone with TsNH2 produces X. Identify the structure of X if it exhibits the following spectral data. All right, the data is like IR, you are having 3290 and 2115 and 1710 centimeter inverse. In NMR, you are going to have like 1, 2, 3, 4 and 5 peaks, and you are given with the option. So in this type of question, basically if you don't know much about organic reaction, let's say I'm not good at organic chemistry, I don't know how epoxy ketone reacts with TsNH2. In that case, now I am going to just rely on my spectroscopic data or the spectral data, and I'll try to utilize that to solve the question. Okay, now in this case you will see that there are 3 bands in IR. If you want to like identify them, it's pretty simple to do. This one is a carbonyl band, right? This is because of CO band. Now this 2115 is the region for C triple bond C stretching, like this is alkyne stretching, and 3290 is for CH single bond stretching. Okay, around 300 or 3300 the peaks which you get is because of either OH stretching, CH stretching or NH stretching. So because you don't have OH and NH, so of course this will be CH stretching, right? Now considering all that thing, you can simply cancel out option number D, because here you don't have triple bond, so you can just cancel out this. Now you are only left out with 3 options. Now IR cannot help you much. This much is what your IR can help. Now the next thing is you have to rely on NMR to look upon further things. Now let's try to assign, let's see how many peaks we are getting in NMR. We are getting 1, 2, 3, 4 and 5 peaks. Okay, so 5 peaks. Now if you look upon the molecules here, how many peaks you are going to expect? So this is going to give you A, B, B, because both of them will be equivalent, then C, D and E, 5 types of peak. I guess in all the options we will get 5 types of peaks, so it is not going to make much difference. So let me erase this. Okay, in all the option number A, B and C, in all of them you will get 5 peaks. Now we have to look upon the NMR results or NMR data to look upon them. So let's look upon it. The multiplicity of the peak or the splitting of the peak is going to help us to find out the next thing. First thing is that in this particular molecule, in all of them, you will see that there is a 6 hydrogen singlet, there is a 1 hydrogen triplet which has J is equals to 3 Hertz, then you have 3 hydrogen singlet which is having 2.15, like that means that this is a particular methyl group. This is because of CH3 group attached to something electronegative. All right, that is fine. Then you have 2.28, 2 hydrogen doublet and J is equals to 3 Hertz. That means that this peak and this are actually coupling with each other. All right, so let's look upon it a little later. Then you have 2 hydrogen singlets. So let's look upon it. So this CH3 group is nothing but this CH3 which you are getting actually in all of them, right? So in all of them you are getting. So if you look upon all these options, what is the difference between all of them? Like what's the major difference between all of them? So in option A and B, the major difference which you find out is that this like this particular carbon which is actually having both these methyl groups like CH3, this is this 6 hydrogen singlet that is just attached to this carbonyl group, and here it is attached more towards this towards the alkene group. It's away from this carbonyl. That is the thing, and here again this is a little bit away from it. So now you have to look upon the stereochemistry with the help of NMR. Okay, so let's start assigning it. So this 6 hydrogen singlet is because of this methyl group. Okay, so let me write down that here it could be like 6 hydrogen singlet. Okay, I'm not writing the chemical shift, but yeah, 6. Since all of these are our probable answer, so I'm just writing in front of all of them 6 hydrogen singlet. All right, now the next thing is that you have this 1 hydrogen, yeah, this one. So this is basically alkyne. Okay, this is terminal alkyne hydrogen, the hydrogen which is attached to the carbon-carbon triple bond. That is why we are getting it. Now one thing to note over here, that it is giving you a triplet. If let's say if this is the hydrogen which we are talking about, it should not give you a triplet, right? Why is it giving you a triplet? Because it is coupling with something having two hydrogen, and that coupling is actually J4 coupling. Okay, now J4 coupling, that's why we have a very less value of J, that is only 3 hertz. So J is equals to 3 hertz is for J4 coupling, and with whom it is coupling? This particular group is coupling with a 2 hydrogen doublet group, means a particular CH2 which is giving you 2 hydrogen doublet. Now let's talk about, or let's look upon them. So if I have to couple them, though this particular hydrogen is attached to okay, this is the one, it should have 4 J coupling, that means one bond, this is the second bond, this is the third bond, and these are the 4 bonds, right? Fourth bond. So basically these hydrogen is what we are talking about. But are these hydrogen going to give you a doublet? No. Why? Because these are two because they are just attached to these two, right? So it should give you 1, 2 and 3, because it will couple with these two and this also. So total, these I am talking about these hydrogen, so they are going to couple with total of 3 hydrogen. They should give you a quartet, or if you compare, if you just see it, so they should not give you a doublet, they should give you a quartet. So that's why it is not going to give you a doublet, and that's the option A isn't correct. Okay, again coming to this particular one, if I talk about this hydrogen, so 4J coupling, just look upon it. So 1 bond, 2 bond, 3 bond, and there is no hydrogen. If I look upon this, and if I say that this is the CH3, so they become at 5 hydrogen away, and 5 hydrogen coupling or 5J coupling does not happen, because coupling can at most happen till 4. That's why J value is very less. A proper coupling looks only up till 3J. But over here, since it is alkyne group, it can like extend till 4 bonds, but not beyond 4. So that is not going to happen in option number B as well. In option number C, it is possible. If you look upon this, this is the hydrogen which we have. Now 1 bond, 2 bond, 3 bond, and 4 bond, right? So it is coupling because of it. Fine. Whether these hydrogens are going to give us a doublet, so because just on the other side you don't have any hydrogen attached to them, they are only going to couple because of this. Each, like both of them are mutually coupling with each other. So this one is giving you a triplet. Okay, so this is giving you 1 hydrogen triplet, and these are giving you 2 hydrogen doublet. That's why. Okay, so did you understood why option A was not correct and B was not correct? So this is the reason. So this is the probable answer, and at the end we have 2 hydrogen singlet as well, and that is because of these 2 hydrogen, because on the adjacent of them you don't have any group to like to split them up. So that's why they are going to give you 2 hydrogen singlet, and that is going to make all the things clear for us, and that's why option number C becomes our correct choice. So it was a little tricky one because of these coupling and all, but you should remember the values. You should understand, or you should just look upon that what are the possible things. Go with the easy one. First of all, cancel out the options with the help of IR, and then go for the NMR. Okay, in the subsequent questions you will see there are more questions in the video where we will discuss these type of things, so you will be able to understand it in much deeper way, right? So this particular question is a typical name reaction. First of all, I'll give you a hint. It says that the NMR spectrum of the compound shows the following peaks. Peaks are given to you. At 1.27 you have 6 hydrogen singlet, then 1.7 you have 4 hydrogen multiplet, then 2.88 you have 2 hydrogen multiplet, 5.4 to 6.1 you have 2 hydrogen broad singlet which is D2 exchangeable, and then 7.0 to 7.5 you have 3 hydrogen multiplet. Predict the structure of the product, and the molar mass of the product is also given to you. This is a particular molecule which is basically a oxime, and you are treating it in the acidic medium. Now do let me know in the comment section what is this, like which name reaction it is. Okay, if you know the name reaction, do let me know in the comment section. I'm not going to tell you that, but yeah, the product which we are going to get in this is not based on the typical that name reaction, like the product which you are expecting through that name reaction. Okay, so that is not happening. There is something else which is happening. So what we are going to do is we are going to look upon the options and with the help of that we will try to like answer it. We will not use any organic chemistry over here, we will not do any mechanism, nothing, but we will just analyze spectroscopic data to find out the correct answer. So let's jump in over here. And whenever these type of spectra are given, first of all go for those which are very distinctive, very understandable. So these spectra, which is 5.4 to 6.1, you have 2 hydrogen broad singlet, and these are D2O exchangeable. Now understand, whenever you have D2O exchangeable like protons, these are generally protons of OH group, alright, or protons of NH group. That's all. These are the ones which are D2 exchangeable. Now of course in the options you don't have any OH group, so you are expecting NH, right? Now here you have 2 hydrogens which are of that type. There are 2 hydrogens which are D2 exchangeable. Now if you look upon option A and option B, in both of them you have just 1 hydrogen with nitrogen. So that means D2 exchangeable should be just 1 hydrogen from both of them. But since in the question it says 2 hydrogen which are D2 exchangeable, so that's why option A and option B you can simply cancel out, because you need 2 D2 exchangeable which is present in option C or in option D. In both of these options you have D2 exchangeable proton, right? Now let's look upon the other spectroscopic data. This 6 hydrogen singlet is very simple and very easy to see. It is going to be because of 2 methyl group which are both in options C and D. So this is like 6 hydrogen singlet is because of these methyl groups, okay? 6 hydrogen singlet, I am just writing, these methyl groups are going to give you that, fine. Next we have 4 hydrogen which are giving you multiplet, okay? 4 hydrogen which are giving you multiplet, fine, let's assign it a little later, and then 2 hydrogen which are giving you multiplet, okay, fine. Then in the aromatic region, if you see, there are 3 hydrogens in the aromatic region from 7.0 to 7.5, that's the aromatic region. So if you look upon option number D, you have actually 4 hydrogens in this aromatic region because of the absence of a plane of symmetry. This particular has 4 hydrogen in this aromatic region, whereas in option number C, if you see, only 3 hydrogens are there in the aromatic region, which goes with the spectroscopic data which we have. So 3 hydrogen multiplet, they are going to split up and they all are shown all together, but they all are staying in the aromatic region. So in the aromatic region you only have 3 hydrogen as per the data, which satisfies option number C, and till here itself you are quite confirmed that your correct answer is going to be option number C. Why? Because you only have 3 hydrogen in the aromatic region. Basically you can go with the option number C, you don't have to know the mechanism and all. Alright, but I will still wait for your comment in the comment section that which name reaction it is. Okay, you have to find out which name reaction it is. Okay, that you have to let me know in the comments. Let's take the next question. Alright, let's take this question. It's again going to be a lot of like spectroscopy to be discussed in this. So the question is from typical NMR spectroscopy. It says identify the structure of the compound that fits best with the following spectral data. See, whenever you do questions related to spectroscopy, I'll suggest you to look upon some specific peaks, okay? With the help of that, you will get to the correct answer, and you don't have to assign each and every peak for the correct answer. I'll let you know in this question how to use that. Okay, so we have various peaks over here. You have 2.06, 3 hydrogen, doublet of doublet, J is equals to 1 Hertz and 1.6 Hertz. So it's basically coupling with 2 protons nearby, okay? Then you have 5.44, 1 hydrogen doublet of quartet with J is equals to 2 Hertz and 1.6 Hertz. Then 5.52, 1 hydrogen doublet of quartet, again J is equals to 2 Hertz and 1 Hertz. Why these all J values are given? Because a single proton is coupling with 2 of them nearby, okay? So that's why so much of J values are given over here. Then you have 4.5 star marked. The star marked is basically D2 exchangeable. So let me highlight this one. So this is a D2 exchangeable, 1 hydrogen broad singlet. Then you have 7.16, 1 hydrogen doublet, J is equals to 9 Hertz, and then 6.88, 1 hydrogen doublet of doublet, J is equals to 9 Hertz. Then you have 10.31, 1 hydrogen, J is equals to 0.4 Hertz. And then 11.22, again 1 hydrogen broad singlet, and this is again D2 exchangeable. So as I told you in the previous question, D2 exchangeable is because of OH group. So basically this 4.5 and 11.22 is because of OH groups. Okay, so in the option you should have 2 OH groups. Now if you look upon all the options, every option has 2 OH groups, so that is fine. Next thing which you have to look, or next thing which is going to specify towards the correct answer is 1 hydrogen J is equals to 9 hertz and doublet. Okay, 1 hydrogen doublet and J is equals to 9 hertz, and if they lie in aromatic region, remember this. Okay, aromatic region is somewhere from 6.8 to 7.2 or 7.3 till you can take. So if you are getting peak in this particular region, and if you are getting J is equals to 9 hertz or 8 hertz with a doublet and 1 hydrogen, this clearly means that this is a case of orthocoupling. Okay, orthocoupling means that the two groups are going to be like, two hydrogens are going to be like this, and on the all the others you will be having different substituents. It doesn't matter, but these two hydrogens should be at the ortho position. Okay, then only you are going to get that, and which I have just highlighted with these ones. These are the two which are going to tell you that. Now if you look upon the option, the orthocoupling is only possible in option number C. Any other option does not have orthocoupling, and that clearly makes option number C as correct. You have not done, you see, so many NMR data was given, so many things was given to analyze, but with the help of just one thing you have you have reached the correct answer. You don't have to assign each and every peak, but still I'll explain you that how you can basically assign the other peaks as well. So yeah, if you look upon this, which is 10.31, 1 hydrogen D and J is equals to 0.4 hertz, this is because of CHO group, right? This is the CHO group, and that's because of this. So 10.31 is the value which you are going to get for this. Now talking about this, that is 2.06, 3 hydrogen doublet of doublet, that's because of methyl. This is methyl. Now why is it giving you a doublet of doublet? Because this is coupling with this hydrogen as well. Okay, this is coupling with this hydrogen, and this is also coupling with this hydrogen. So cis coupling and trans coupling, both of them are happening, and that's why you are getting two different J values. For cis coupling you are getting J is equals to 1.6, and for trans coupling you have J is equals to 1.0. So that's why you are getting this, this methyl is giving you doublet of doublet. Now why this is giving you doublet of quartet? That is because this hydrogen is again coupling with this hydrogen. This is geminal coupling, that is at J is equals to 2 hertz, and then a cis coupling which is 1.6 hertz because with this particular methyl. So due to coupling with methyl it is giving quartet, and due to coupling with this hydrogen it is giving a doublet. So doublet of quartet. Same explanation goes for this as well. Now here you are going to get a geminal coupling and a trans coupling. So geminal coupling is giving at 2 hertz and that is giving you a doublet, and this trans coupling is giving you at 1 hertz, and which is giving you a quartet. So basically doublet of quartet. So we have assigned 1, 2, 3. This peak I already said that it is for the OH group. This is for your like aromatic region. So this is for the benzene ring, like the hydrogens of these benzene rings are those, and these and this is for CHO, and this is for OH. So that's how you have assigned all the protons. So it is very important to look for some specific peaks to reach out to the correct answer. In NMR, that's the beauty of spectroscopy. You don't have to know every bit of it. Just with the help of limited information, or just with the help of limited knowledge, you can solve the question. Let's take the next question. Alright, let's look upon this particular question. It says identify the product in the given reaction, exhibit the following spectral data. You are given with a particular molecule. It is reacting with two reagents. The first one is SOCl2 in the presence of triethylamine, and then you have water. Okay, so for the, I think for the workup it will be used, and it says that you have mu max at 1730, then you have the proton NMR at 1.12, 6 hydrogen singlet, then 2.8 at 3 hydrogen singlet, 9.8 at 1 hydrogen singlet, and then you have for your carbon you have at 202 at 45 at 22 and 15. That means 4 carbon signals, and there are only 3 hydrogen signals, one carbonyl peak you are getting. Okay, so now that's what they have given you, and they are asking you to find out that what is going to be the correct answer. So see, again, this is a typical example where neighboring group participation and all will happen, and there will be a hydrogen abstraction followed by there is going to be intramolecular nucleophilic attack to give the correct answer. I'm not going into the organic reaction of it, or I'm not going in the mechanism of it, just for the sake that I don't want to make this question so difficult that if someone sees the solution it feels like, oh, it's so difficult to approach. I will give you an easy way how to do these type of questions. Okay, see, you don't have to worry about the reactions. Whenever you are given with organic spectroscopy, in 99% cases you don't have to worry about the reaction. What is happening doesn't matter. Only what you have to look upon is the spectral data, and you have to see that which option matches it. Alright. Now, considering that, if we see it, let's first of all talk about IR. So IR is at 1730, that means we have a carbonyl carbon. Now, if you look upon the options over here, you have in option number A, you have OCHO, which is basically a ester group. It becomes like ester group, right? C double bond O and H, yeah. So it becomes a ester. Here also it becomes a ester. In option C and option D, this remains a ketone, right? Yeah, fine. So that is one thing. Next, we have proton NMR. In that, you only have 1, 2 and 3 types of protons. So if you look upon option number A, yes, of course, you have both these of same type. So A type, B type and C type. Only 3 types of proton. In all the options, I guess only 3 types of protons are there. But if you see the carbon 13 NMR, there are 1, 2, 3, 4 peaks. And now, due to presence of aldehyde, of course, this is what you are getting. This is because of aldehyde. So your option number A becomes incorrect because this is giving you a ester group over here. Why I am telling you a ester group? Because O, C double bond O and H, that's what your CHO is. So this overall becomes a ester group. So this is a ester, this is also ester. So option A and option B you have to simply cancel out. Due to IR, you can simply cancel it out. You have to look for aldehyde now. So aldehyde is only present in option B and option C and option number D. Let's look upon NMR now. Now, if you see the NMR spectrum of these molecules, you will find out that these methyl are going to give you 6 hydrogen singlet. Fine, proton NMR I am telling you. Then 2.83 hydrogen singlet is because of methyl attached to some electronegative group. Okay, so that is because of MES. Okay, one more thing, that OMe or OCH3, it has a very distinctive chemical shift of 3.2 to 3.5 ppm. Okay, this is the value because of high electronegativity of oxygen. You have very high, or the chemical shift of methyl group, these hydrogens. Okay, they are going to give you 3 hydrogen singlet, and at this particular range, in this particular range. And since here this methyl is attached to sulfur, so that means that this 2.83 hydrogen singlet cannot be this one. This is OCH3 again, and it should have been something, you know, something around 3.2 to 3.5. That is one thing, or that is one way how you can neglect option number D. Another way is that this could be sulfur attached to methyl, because sulfur is less electronegative than oxygen. That's why the chemical shift will not go till 3.2 but around 2.8. This 9.8 is because of the aldehydic hydrogen, which is this. Okay, so 9.8 is because of this. This is 2.8. Now let's look upon carbon NMR and let's see whether it satisfies. So here you have 1, 2, 3, 4 carbon NMR signals, which will be here. All the 4 carbons are different because they are in different chemical environment. Whereas if you look upon this, you will find out, like, see, here you have 1 carbon, 2 carbon, 3 carbon, and these 2 are equivalent ones. So these are of 4 types. And over here, if you see, this is again 1, 2, 3 and 4. They are 4 different types of carbon, but still the thing is that because of this NMR, or because of this particular chemical shift, you can neglect option number D. Okay, that's how you can cancel out option D, and option C becomes your correct choice. So this value was the distinctive value, or you can say the deciding factor how we reached to this. So IR has helped us to cancel out 2 options, and then a particular NMR has helped us to reach out. Alright, mechanism for these reactions and all the things are there in my ebook. If you are willing to purchase that, again the link is there in the description of this video. You can get the copy of that ebook. It's a PDF file, you can download it and you can see the solution of this particular, right? Let's take the next question now. Okay, here comes the easy ones. It says that the number of proton decoupled signals that will appear in the 13C NMR for the following molecules are. Whenever you are given with this type of molecule, the easy way is to find out the like plane of symmetry. So if I draw for this molecule, this is a plane of symmetry. Now anything which is on one side of this plane is going to be similar to the other side. So if this is of type A, this is also going to be of type A. Okay, they are talking about carbon NMR, so we'll just look for carbons. If this is a carbon of type B, this will be carbon of type B. This is of type C, type C, type D, type D. So you got 4 types of carbon in the first option. You can cancel out option A and option C because they are telling 5 and 2. They are not going to be the correct answer. Okay, so either option B is correct or option D is correct. Now look upon the second molecule. See, this molecule is easy to understand if you draw it in a planar form. Okay, right now it is in 3-dimension form. Let's draw it in planar form. So let's number it 1, 2, 3, 4, 5 and 6. We have a 6-membered ring. So let me make a 6-membered ring. Let me number it up 1, 2, 3, 4, 5 and 6. Now 1 and 4 is attached by 2 carbons. Let's call them as 7 and 8. So 1 and 4 is attached by 2 carbons. Let's call them as 7 and 8. This is how you can make it in the planar form. Again, once again you have to make a a plane of symmetry. Now you have to assign the carbon on one side will be similar to the carbon on the other side. So one thing which is little different over here is that presence of an axis of symmetry. Axis means if I draw a line like this and if I start rotating it, basically this carbon and this carbon, they all are going to rotate in the similar fashion, or they are going to interchange their positions. It's just like the wings of the fan. Okay, in the same way, these back side, this carbon and this carbon are going to interchange their position. What I'm trying to say is, if I draw a axis, like this and rotate it, so basically carbon 6, 7 and 2 are going to interchange their positions, and carbon number 5, 8 and 3 are going to interchange their position. So that means that if I name them like this, so if I name it as carbon number of type A, because I am rotating them, and that's why 2, 7 and 6 become of same type. So this is also going to be of type A and this is also going to be of type A. Why? Because of the rotation. Okay, so if this is of type A, this is also of type A, this is also of type A, like that. Since there is a plane of symmetry, so I told you like on the other side of plane, same things are similar things are of similar type. So this will also become of type A, the other thing is of type A, this is also of type A. Alright, and now you have assigned it. Now the other thing is only this bridgehead carbon, this is of type B, and because of the plane of symmetry, this is going to be of type B. The only type of, like, how many types of carbon we have got in this? Only 2 types of carbon. Okay, so type A and type B. So now you have reached to the correct answer, which is option D. But still, let's check this option number 5. Again, I told you that number it up. So 1, 2, 3, 4, 5, 6, 7. Okay, you have to make a 7-membered ring. Okay, so 1, 2, 3, 4, 5, 6 and 7, and with 1 and 5 you have to join with a carbon. Okay, so we have done it. Just this carbon, this is, let's say, 8, so this is the. Now what I have to do is I have to make a plane of symmetry, if it is possible. Yes, I can make it like this. Now I have to number it up on the other side of. Now here rotation is not possible. Why? Because if you try to rotate it, this side only 2 carbons are there, this side 1, 2, 3 carbons are there, so they won't rotate. Here we were having equal number of carbons, 2, 2 and 2 on every every side of that bridgehead position. So that's why rotation was possible. Here you cannot rotate. Now if I try to name it up, so if this is of type of carbon of type A, this will also be of type A. If this is of type B, this is also going to be of type B. If this is of type C, this is also going to be of type C. if this is going to be of type D and this one is going to be of type E. So total we have got 5 types of carbon. So that again clarifies that option number D is correct. Why I have given this question? Because it is very important to practice all these type of molecule. Many people do mistakes while doing them in exam. Alright, take the next question now. Alright, let's look upon this question. Here it says using the following proton NMR spectrum, determine the most probable structure of the compound. Now here you are not given with data but a spectrum itself. If you look upon it, or if I zoom it a little bit, you will see that how many signals you have. You have 3 signals, okay, signal number 1, signal number 2 and signal number 3. Signal number 1 is a quartet, signal number 2 is a singlet, and signal number 3 is a triplet. Okay, this is a 0 scale, so this is the TMS peak which they are telling you. Signal number 1 is somewhere around 3.9 ppm, that's what I can say. Signal number 2 is somewhere around 2.5 ppm, right? And signal number 3 is somewhere around 1.4 or 1.3 ppm. So from spectrum we can just we have just understood this much. Now the next thing is to look upon the molecules itself and see which is the correct answer. To answer this question, just see there are very less spectrum and the options have so many number of carbons. So that means the molecule has to be highly symmetrical in order to attain it. So just 3 signals, you have to look which option is going to give you 3 signals. Let's look upon option number A. How many signals you are going to get? So signal A, because both of them will be equivalent, signal B, C, D, E. So you are getting 5 signals here, which is not according to the option. Now let's look upon this one. This is again a highly asymmetrical molecule. That is because if I draw it properly, this is CH3, CH2, C double bond O, then you have CH2O, CH2, C double bond O, O, CH2, CH3. Now if you number it up, so this is type A, type B, type C, type D, because all of them are different, then type E and type F, 6 type of signals, which is not correct. You see the molecule is not symmetrical actually, so option number B is also incorrect. Option C, if I draw it, so it is CH3, CH2, O, C double bond O, CH2, CH2, C double bond O, O, CH2, C. This is one of the most symmetrical molecule which we have got till now. Okay, and if I see the option number D also, so here also you have, see it's not quite symmetrical because it's here you have 3 carbons, here you only have 2 carbons, and that's why it's not symmetrical, right? So yeah, that makes this option also different, like it's asymmetrical molecule, option number D. You can cancel out option D as well. How many types of carbons you have? So here this is carbon of type A, type B, type C. Then since this is a symmetrical molecule, so this is going to be of type C, type B and type E. So that's how you have assigned 3 signals you are only getting in option number C, and that's how option C is correct option. So although the question looks little tricky, a little difficult, but once you look upon it, once you dive into it, it becomes easy to solve. So that's what, and that's how it will be done. Let's see the next question. Alright, so this is again a question from 18 aniline, and it's from the NMR spectrum of that. It says which of the following signals are shown by the proton NMR spectrum of aromatic compound 18 aniline. It says one signal at 7.6 ppm singlet, one signal at 4.5 ppm singlet, 2 signals at 9 ppm and at 3 ppm. Then says then says 3 signals at 9 ppm, minus 4.5 ppm and 3 ppm. Okay, so let's look upon it and let's see what will be the correct option. First of all, let me draw this 18 aniline first quick. Alright, so this is how 18 aniline looks like. If you count them up, there are 9 carbon-carbon double bonds. They are all in conjugation. It's an aromatic molecule. Now, if you see how many types of hydrogen you have, because the number of proton NMR spectrum is actually going to depend upon how many types of hydrogen you have. So you have like outer hydrogens, which are actually 12. If you count them up, these are 12 outer hydrogens and there are these 6 inner hydrogens. So you have 12 outer hydrogens and you have 6 inner hydrogen. So that means you have 2 types of hydrogen, and simply if you have 2 types of hydrogen, then you should get 2 signals. The outer ones are de-shielded, you should know this, as they are de-shielded, whereas the inner ones are shielded, and that's why they give you chemical shift at little higher value, around 9 ppm, and they will give you chemical shift at lower values. They give you at minus 3 ppm. Okay, so they give you at very low chemical shift. So that's why correct answer is option number. That's how it will be done. So you have to study about annulenes, 14 annuline and 18 annulenes. These are mostly asked. So just look upon the NMR spectrum of them. How many types of hydrogens are there and what are the chemical shift values of them. Okay, that will make it very easy for you if the questions are asked in exam. Let's take the 10th and the last question of this particular video. It says that the mass spectrum of the following compound shows the base peak for the fragment formed by the McLafferty rearrangement. The m by z value of the fragment is. Now this is from the mass spectrometry. A molecule is given to you. They are telling you that what the fragment which will be formed by McLafferty rearrangement, what is the m by z value of it. Okay, so that's what you have to do. So you have to perform McLafferty rearrangement and then look upon the option. Now you all know that in order to have a McLafferty rearrangement, what you need is a conjugated system, like a hetero system, CO bond, CN bond, all these things, either of them, and then you need a gamma hydrogen. So in this molecule, if you look upon, so I have 1, 2, 3, 4, 5 and 6 hydrogens, right? That's what I have. Oh, sorry, 5 and 6 carbons. So I can basically write it like this: C triple bond N, right? Because this is what my CN group is, and then I have CH2, then I have CH2, then I have, okay, this is 2, 3, then I have CH, and then I have CH3 and CH. So am I correct? 1, 2, 3, 4, 5 and 6. Yeah, I am fine now. Now let's try to assign the naming of them. So if this is the group which you are talking about, so this is the alpha group, this is beta, and this is gamma. Now since the gamma carbon you have seen, so this is gamma hydrogen, and this is the one which is going to undergo McLafferty rearrangement. Now if you see this, so what happens that this bond goes to this particular position. This bond shifts over here and this bond is going to break. So basically the bond between alpha and beta group breaks down. A new hydrogen is going to join to the hetero group, which is over here, either oxygen or nitrogen, whatever is here, and a new double bond is formed between the carbon species and the alpha group. Okay, so that's what is going to happen. So what we are going to expect is C double bond NH and then C double bond C, ketene kind of thing. Okay, and along with that you are going to have CH2 double bond C and CH3, and so these are the two fragments which you are going to get. What they are asking is the m by z value. So if you calculate the m by z value of this, these carbons are having mass of 12, nitrogen has mass of 14, hydrogen has mass of 1. If you do that maths, you will get 41 m by z for this, and if you calculate for this, this is 14 plus 12 is going to give you 26, and if you add 30 to that, 26 and 30 is going to make it 56. So this is going to give you m by z of 56. So 56 is not in the option, 41 is in the option, which is the one, and that's option number C is the correct option. So the McLafferty rearrangement base peak is going to be for this, because this is the most stable fragment which you are going to get, and that's why this is going to give you the base peak at 41. So this is further going to undergo fragmentation to form methane and allene. So that's why this is not going to give you the base peak. base peak will be over here, which is at m by z41, and that's going to be the correct answer. So that's all for this video. Thank you so much for watching. We have done 10 questions which were different, which were challenging, which were having tricks to solve, and that's what I have tried to do in this particular video. I hope you all liked the concept. If you have liked the concept, please do let me know in the comment section. It takes a lot of effort, lot of time, and lot of energy to compile the concept, to compile the questions, and to present it in front of you. Please do please do let me know, please do give your feedbacks in the comment section below, and do let me know what topic you want me to cover in the next upcoming videos. And you can follow our channel on Facebook, Instagram, or Twitter as well. The link are there in right in front of your screen. So thank you so much for watching. I will see you in the next one. Till then, have a great day. Bye bye, take care. Hey guys, so I teach live on Unacademy Plus platform. Here I teach for the CSIR UGC NET category, and you can follow me over here for regular classes. You can access my free classes as well as my paid classes on this particular platform. The classes which are free, you can get that under the section of special classes, whereas in order to access my paid classes, paid live classes, you have to take Unacademy Plus subscription. So do make sure that you take the Unacademy Plus subscription to access all my paid classes, which are quite organized. The whole syllabus is being completed over there, and the classes are quite regular over there. So make sure that you take Unacademy Plus subscription by using my referral code, that is n_huda. That's it for this. Thank you so much.